Hello, welcome to a video about lasers. I've got a couple of shots from The Simpsons where there's some lasers involved, but the photo in the background is from Rainbow Serpent, which is my #1 favourite festival in the entire world. It's a nice little dance music festival and they've got some cool light shows whilst the music is playing at night time. It hasn't been on for a couple of years, obviously because of the pandemic, but it's usually held in summer, and unfortunately in 2019, 2020, that beginning and end of the year kind of time, the venue was impacted by the bushfires, so haven't been able to go for a while, but hopefully it does bounce back, even though it's been a rough couple of years for it, and I doubt it will go ahead this year because it's probably a bit too late to organise. Anyway, this video isn't about that, it's about lasers. So when a photon with energy corresponding to a transition from a higher energy state to a lower energy state is incident on an atom that's already in a higher state, it can stimulate a transition to a lower state. This results in two identical photons, the original photon that was incident, and then a second photon that results from that stimulated transition. The photon emitted in stimulated emission is identical in energy, direction and phase to the incident photon. In stage 2 physics, you need to be able to compare the process of stimulated emission with that of ordinary, or just called spontaneous emission. So a couple of definitions. Spontaneous emission is the transition of an atom from an excited state to a lower state via a photon emission. So this is the kind of emission that we've been talking about in the videos leading up to this one. It usually occurs after around 10 to the negative 8 seconds or within 10 to the negative 8 seconds of an atom being excited. So it happens very quickly after an electron absorbs energy in the first place. Stimulated emission is the stimulated transition of an excited atom to a lower energy state, or an electron to a lower energy state, by a photon that has energy equal to the difference in energy, that triangle E means difference in energy, between an excited and lower energy state. So for some reason there's this phenomenon where if an incident photon is equal to the energy difference between two energy levels for an electron, then that electron will emit a photon. They obviously the exact same photon because the energy differences are the same. So for some reason this occurs. So as a result, at the end of stimulated emission, you get two identical photons with the same energy, direction, and they're both in phase. So one photon is the original incident photon that caused the stimulated emission, and the other photon is the photon that results from the stimulated emission. So in our diagrams here, we've got, so this is when the electron becomes excited, the atom is in its excited state, so that's just some energy that the electron absorbs, and then it moves up to its excited state. This here is spontaneous emission, where after about 10 to the negative 8 seconds, a photon is emitted, and the electron moves back down to its ground state or lower state. In stimulated emission, we have an incident photon here, and then we'll have two photons that result from this, the original incident photon as well as the photon that corresponds with the energy that's now been emitted by an electron as it goes back down to its lower state, so as it's stimulated to revert back to that state. I'll read the learning intentions for lasers now. Lasers use the process of stimulated emission to produce electromagnetic radiation. In many lasers, stimulated emission occurs from atoms that are in a higher energy state. A population inversion is produced in a set of atoms whenever there are more atoms in a higher energy state than in a lower energy state. For practical systems, the higher energy state must be metastable if a population inversion is to be produced. The energy carried by a laser beam is concentrated in a small area and can travel efficiently over large distances, giving laser radiation a far greater potential to cause injury than light from other sources. And in stage 2 physics, you need to be able to explain how stimulated emission can produce coherent light in a laser. You need to be able to explain the conditions required for stimulated emission to predominate over absorption when light is incident on a set of atoms. You need to describe the useful properties of laser light. So that means that the properties are that it's coherent and monochromatic and maybe of a high intensity. And you also need to discuss the requirements of the safe handling of lasers. So we'll cover all of those success criteria in this video. To begin with, LASER is actually an acronym. LASER stands for Light Amplification by the Stimulated Emission of Radiation. They produce, or a laser produces, a narrow, intense beam of coherent light via stimulated emission. And as a reminder, coherent means light that is the same frequency, same direction, and the waves are in phase. So each point of the wave matches up with all of the other waves that make up that laser light. On your next page, or your next slide rather, you've got a table with a bunch of different features and the function of each feature. I'm going to keep the slide in this video on this diagram, and I'm going to talk about those features, and you can just refer to that table. And these features and their function will correspond with explaining how stimulated emission can produce coherent light in a laser. So the first feature that we'll look at is the gain medium, or sometimes called the gas reservoir, and this contains atoms or molecules that emit light via stimulated emission. So this is just full of, the molecules or the atoms that you need for the stimulated emission to occur, because you need atoms to be being excited for this to actually happen. So that's what your gas reservoir is, or your gain medium. Gain mediums can be dyes, they can be gases, they can be solids. You can use carbon dioxide, argon, krypton, a mixture of helium and neon. You can use liquids like methanol, ethanol, etc. So there's loads of different things that you can use. You can use like sapphires and rubies as well, so lots of different things. The main property, I suppose, that you need is that whatever the medium is contains molecules or atoms that will be excited and that will emit light via stimulated emission. The next features that we'll look at are the anode, the cathode, and the pump, which is just the potential difference, or the voltage, and the voltage is connected to the anode and cathode. So collectively, this system, which is just like a potential difference basically, it does work on the gain medium atoms, and this is what raises them to their excited state. So the potential difference between the anode and cathode does work on the whatever you've got as your gain medium, and because it's doing work on them, it's transferring energy to them, it's raising the electrons to an excited state. The atoms will then, that have been excited, will then release their photons via stimulated emission. The next feature is the full mirror, and this is at the, non-light emitting end, or non-light beam emitting end of the laser. This reflects all photons into the laser cavity, and light is amplified via stimulated emission as well as constructive interference. And then we've got the partial mirror up the other end, and this permits transmission of 1 to 2% of the photons that have been produced by stimulated emission via a partially transparent aperture, and that's where the narrow output beam comes out of. So the mirrors are reflecting most of the protons back and forth, and they're causing stimulated emission and then interfering constructively. But in the partial mirror there is a small aperture where the laser beam will come out of, and that's the 1 to 2% of photons that are they just happen to be hitting that particular part of the mirror, which is like an aperture or a hole or like a gap in the reflective surface. In a couple of slides there's a diagram that kind of ties this whole thing together, so we'll look at that in a moment. So that's everything that we've just gone through. There are some required conditions for coherent light production via stimulated emission. One of those is that you need an inverted population to be produced, and what that means is that more atoms are in the excited state than in the ground state, because if you're going to have stimulated emission occurring, your atoms need to be in that excited state for that emission to occur or to be stimulated. So by having an inverted population, you ensure that photon emission dominates photon absorption. So if all of your gain medium atoms were in the ground state, then they'd be absorbing energy or absorbing photons that have been emitted, and then you'll get a net photon absorption throughout your gain medium. So you want your gain medium atoms to generally be in the higher energy state or excited state, so that when a photon is incoming, it's causing the stimulated emission. So I might draw that. So you've got an incoming photon, you've got your electron that's nice and excited up here, the photon is incoming, and then as a result the emission is stimulated, so this electron comes back down here, and then you've got your incident photon that continues on its merry way, and then you've got your emitted photon or your stimulated emitted photon. In this diagram here, this would be called a normal population, where most of the electrons are in the ground state. So you want an inverted population where most are in the excited state. Another condition is that the higher energy state needs to be metastable. And this is when electrons remain in a higher energy state for longer than usual. So rather than being in their excited state for about 10 to the negative 8 seconds, they're a bit slower to come back down, so closer to 10 to the negative 3 seconds. And this ensures that electron transition occurs via stimulated emission rather than spontaneous emission. So if everything's occurring via spontaneous emission, you're obviously not getting that stimulated emission. So having metastable elements means that the electrons are remaining in their high energy state for a bit longer to allow time for that stimulated emission to occur. To be an effective gain medium, one or more of the elements or compounds that make up the gain medium in the laser cavity must be metastable. Amplification occurs when photons released from stimulated emission cause other metastable excited atoms to emit a photon with the same frequency, direction, and phase. So the waves will be coherent. This process stacks, so photons that have been emitted as a result of stimulated emission can then go on and cause stimulated emission in other excited atoms, and then more photons will be emitted, and so on and so forth. The photons multiply, and they also reflect back and forth from the full and partial mirrors, so you get a bit of constructive interference as well as lots of stimulated emission occurring. So in our image here, this represents the whole process that we've been discussing. So in the first image, this represents or demonstrates a gain medium in its ground state. So all of the atoms are in their ground state. Then you get population inversion with the majority of the gain medium atoms becoming excited. So in our third image, we've got some spontaneous emission occurring, which then goes on to cause stimulated emission. And then stimulated emission stimulates further stimulated emission, or causes further stimulating emission, as we can see in the fourth image. And then your photons will be reflecting back and forth off the full and partial mirrors. That will cause amplification, and then some photons will exit through the partial mirror's narrow aperture, and that will be as a coherent beam of light. So that's why laser light doesn't spread out, it's just very focused at the same point. Whereas if you were to have just a regular like incandescent bulb shining through a small aperture, that light would spread out. Some useful properties that you might need to describe as per the third success criteria are lasers' power output. This can be highly variable, so you can get lasers that will have a power output in the milliwatts all the way through to terawatts. So you've got a range of applications that you can use these different power outputs for. Laser light is monochromatic, so just a reminder that means that it's got a single, or it's comprised of a single frequency. And knowing this frequency allows for technologies that rely on the use of a single frequency of light. So if you've got a situation where you do need a single frequency, then lasers are perfect for this. Laser light is also coherent, as we've been talking about. So that means that laser light has the same frequency, or that it's monochromatic, but that it also has the same direction and the same phase. So all of the waves are at the same point in their path, or the same point in their wavelength. And this means that photons maintain a constant phase relationship over large distances. Physically, this means that laser beams are highly focused and they're unidirectional, so unlike incandescent light, as I was just talking about before. And the last properties that we'll touch on are their high intensity of laser beams and the unidirectionality. And this means simply that the beam doesn't diverge over long distances. So because these beams can be highly focused, and you can have very small, precise laser beams or laser points, this allows for high precision. So if you need very accurate or very precise measurements for machinery, surgery, working on a micro level, the high intensity and unidirectionality of laser beams will allow for this. And lastly, in terms of laser safety, so the safe handling of lasers, some precautions that you would need to be aware of are avoiding eye contact with lasers. So to mitigate this, it's best to use lasers in a well-lit room with effective eye protection, and to direct laser beams away from people so that you're reducing the likelihood of accidentally getting someone in the eyes with the beam. Avoiding skin contact as well as another precaution, and you can reduce the likelihood of this by wearing or covering your skin with protective clothing to avoid any potential burns. Avoiding reflective surfaces is another precaution. Because the intensity of incident and reflected beams are equal, if you're shining a laser onto a reflective surface, you have less intuitive control, or less of an intuitive idea of where that laser beam is going to be reflected. So avoiding reflective surfaces will prevent accidentally hitting someone in the eyes or on the skin. And then also avoiding combustible, so directing laser beams away from flammable or combustible materials will reduce any chances of combustion or fire. Laser beams can obviously have high energy, so it could be enough to spark something that will readily go up in flames.